Alright, let's take a look at this op-amp configuration. So in this case we see we have 4 different op-amps, and we are told to find our Vout at the end of this circuit. Okay, so again, looking at this, initially it looks kind of complicated, but if we break it down into its smaller components, we see that it's actually a pretty simple circuit. So a couple of things to note is the very first op amp here, this guy, you see there's no feedback resistance, as well as this guy, there's no feedback resistance, and this is indicative of a voltage follower. So these two guys, these are voltage followers. Okay, and essentially what that means to us is that our V output is simply our V input. Alright, so meaning we can just write down here we're having a 700 millivolt input into the second stage of this, and then here 300 millivolts coming in here into that second stage. So we've just eliminated those first two op amps, right? And just by the definition of a voltage follower. So now we just have to deal with two other op amps, and if we look at the second op amp here, we'll see that this is actually an inverter. This guy, the second stage here, this is an inverter. Okay, and then look at the third stage. We see that this is just a summer. Okay, so again, this is how you want to break down these circuits. Of course, with the inverter, I'll go ahead and write this down here. Inverter, you'll end up memorizing these equations. V output is equal to minus the feedback resistance over R1 times V input. And then for the summer, in this case, if we look at it, we're going to have two inputs for the summer, so our V output is going to equal to negative RF over R1 times V1 plus RF over R2 times V2. Okay, so this is what we're getting here. So now we've essentially broken down something that looks complicated, or overly complicated possibly, to something that's doable, that we've been working with a bunch of equations and a bunch of examples, excuse me. So let's look at this. Let's break this down. So like I said, we have 300 millivolts coming into this inverter, so let's go ahead and work that out. To do that, at the inverter, let's go ahead and write this equation. Let's just say the output of this inverter is going to be out here, so we're going to say the output of the inverter is going to be right here. So let's go ahead and solve that. So V output, and I'm just going to say for the inverter I, just for my convention, it's just going to be my feedback resistance negative 80 over 20, and our input we just said was 0.3. all right, that's where that purple node is, so this is what's going to come out there. All right, then the next thing we're going to do is we're going to say, well, this V0I, or whatever you want to name it, I'm just going to say it's going to be my V1 into my second stage of the amplifiers there, and let's go ahead and plug that in. So I'm going to say V output, and now we're talking about the yellow the actual output we want to solve for, is going to equal minus our feedback resistance here is 80 over 40, all right, times V output I over the inverter, plus again 80, and the second resistance we're going to say is 20. V2 we're going to call our 700 millivolts, so we're going to say 0.7. Okay, and now it's just a matter of plugging in this guy for what we solved for previously. Okay, so if we plug this in, we get our V output equals minus 80 over 40 times minus 80 over 20 times 0.3, all that in parentheses, plus 80 over 20 times 0.7. If we do the math right, and we don't make any errors in the signs, we get 2.4 minus 2.8, and this will give us minus 400 millivolts. Okay, and this is our V output of this entire circuit here. Alright, and that's how you solve this problem. Again, break it down into feasible, recognizable pieces, and then just work your way forward through the stages of these cascaded operational amplifiers.